Good afternoon, everyone. I'm Bon Jing from Xianjiang University, and I'm very glad to be here today to share with you an interesting project we've been doing recently. And in this project, we try to use the ultrafast ultrasonography to visualize and record and even mirror the vibration of the larynx. So, first of all, I would like to give a brief introduction about the larynx. The larynx is the primary voice source for human beings, and the most important parts of the larynx is a pair of vocal folds, and it's driven by the airflow from the lung, and it could vary at a frequency from 100 to 400 hertz during voicing. And a lot of techniques have been introduced to visualize the vibration of the vocal folds and the larynx. High-speed radio endoscopy is one of the mostly widely applied techniques because its major advantage is its high frame rate. It could reach 4,000 frames per second. However, only the supra surface of the vibrating vocal folds can be visualized by using the high-speed video. So in order to visualize the vibration of the tissue below the mucosal surface, researchers have introduced the beam mode ultrasound imaging. And however, the conventional beam mode ultrasound imaging, the frame rate is only dozens of frames per second, and it is way slower than the speed of the vibration of the larynx. Here I also want to introduce another technique that we used later, and it's called electroglottogram, and basically it can be used to record the contact area between a pair of vocal folds during the vibration. In order to increase the frame rate of beam mode ultrasound imaging, my colleagues have tried to narrow the field of view down to 7.6 millimeters, and that means only the vocal fold is included in the view, and the frame rate was increased to about 800 frames per second. However, we thought maybe it is still not fast enough to catch the vibration, so we further increased the frame rate by utilizing the stroboscopic effect. That means the a period of high frame recordings is reconstructed by several low frame recordings. However, this method requires the larynx to stay in the state of quasi-periodic vibration. That means the subjects have to keep their voice at a steady state. So if we want to investigate the unsteady state of voicing, the actual frame rate of the ultrasound imaging should be much higher than this. And then we thought, why not use the plan wave ultrasound imaging here? So its major advantage include that the field view could be as wide as the full aperture size of the linear array, and the frame rate was much higher. So that is why this technique is also called the ultrafast ultrasonography. And in this study, the frame rate was set to 5,000 frames per second, and no compound is used because the larynx, the vibration frequency of the larynx could be from 100 to 400 hertz, and compounding could cause image blurring. The beamformer we used here is a standard delay and sound beamformer, and we also want to try to extract the vibration waveforms of the laryngeal tissues, and the motion estimation algorithm we used here is one-dimensional normalized cross-correlation method, and that means only the displacement along the horizontal direction is obtained. So first of all, we should have an idea of what we are looking at. Although the image quality the image quality degrade a little bit when we try use the plan wave imaging. The edge of the vocal fold and the fast vocal fold still can be identified as two short echoey curves. And then we could locate the body of the vocal fold, which is here, and also have an idea of where is the supraglottal region and subglottal region here. And here is the frame series we got, and these 8 frames of ultrasound images are captured at four different phases across two vibration cycles. The electroglottogram down here and the ultrasound images are captured simultaneously so that we could locate each frame on the time axis here. And here you may already find out that this is the echoey curve of the edge of the vocal fold. And the edge of the vocal fold changes rapidly during the vibration because the vocal fold vibrates intensely during voicing. And on the other hand, here the fast vocal fold seems don't move at all. And so we want to make sure whether it vibrates or not. So we try to measure the vibration of laryngeal tissue at multiple locations, and these locations are pointed out as 4 colored dots in the frame number 1. The blue dots at the supraglottal region, and the green dot at the vocal fold body, and the red dot at the subglottal region, the magenta dot at the vocal fold edge. So here is the waveforms we got here, and as you can see that from the vibration waveforms of the supraglottal structures and the subglottal structures, we can see that there is an obvious transition from the static state to steady and periodic vibration. Because the subjects were asked to start voicing from quiet breathing, and on the other hand, the vibration waveforms of the vocal fold body, which is here, and the vocal fold edge here, seems chaotic and against basic mechanical principles. So here you may ask why, and first, actually, the vibration velocity of the vocal fold edge could reach more than a meter per second, and the shape changes rapidly during the vibration. And it could cause severe signal decorrelation when we try to use the cross-correlation function to track tissue motion. And actually, the cross-correlation coefficient at the vocal fold edge, you can see that drop below 0.8, while at the supraglottal and subglottal structures, the cross-correlation coefficient could be much higher than 0.98. And on the other hand, the cross-correlation coefficient at the vocal fold body is about 0.9. It is not too low, and we thought maybe the decorrelation is not so severe. So the question here, why the waveform still appears so chaotic? So we can go back, see the previous slides here. Here you can see that it is the body of the vocal folds, and it appears much darker than the other structure like the supraglottal region and the subglottal structures around it. So my guess is that maybe the problem is that the echo signal from the vocal fold bodies is so weak, and maybe cause the displacement estimation problem. So then we try to compare the signal to noise ratio at multiple locations. And we can see that here is the signal to noise ratio of the vocal fold body is significantly lower than other structure like the subglottal region and supraglottal regions. And according to a previous study, although the cross correlation is high above 0.9 in the vocal fold body, the estimation of the displacement could be still unreliable when the signal to noise ratio is too low. And we also try to improve the signal to noise ratio by changing the emitting frequency, but it seems it didn't work. Here is the summary of this. From this preliminary study, we can learn that the vibration of the vocal folds can be visualized by using ultrafast ultrasonography. And unfortunately, it is unable to extract the vibration waveforms of the edge of the body of the vocal folds due to decorrelation and low signal to noise ratio. But we are able to extract the vibration waveforms of the sub and supraglottal structures, and the high frame rate of ultrafast ultrasonography enable the quantification of periodic vibration as well as the unsteady state vibration at such as the onset of the voicing at a high sampling rate. And in the end, I want to thank all my colleagues and National Natural Science Foundation of China. And again, thank you all for your attention here. That's all. Thank you.